In this video, we're going to identify the symmetries of all vibrations in a molecule using character tables and group theory. So the molecule that we're going to be looking at is PF5, and we can see that this molecule is a trigonal bipyramidal species, so it has D3H symmetry. And so the first step that we're going to want to do is we're going to figure out what happens to all of the different atoms when we apply the different symmetry operations. And so the first symmetry operation that we're going to apply is the identity, and so in that case all 6 of these atoms are going to stay in place, so we'll get a value of 6 in that case. So for a C3 vibration, if we look at the molecule, we can see right here the C3 axis goes through this fluorine, phosphorus, fluorine axis right here, and so if we do that rotation, these 3 fluorines move. However, this fluorine, this phosphorus, and this fluorine remain in place, and so we have 3 atoms that stay put. Now we're looking at the C2, so it's going to be the C2 perpendicular to the C3 axis, and so it's going to go through the phosphorus fluorine bond, and there's 3 of them, but we only have to focus on 1 of them. And so if we apply the C2 rotation here, this fluorine, this fluorine, this fluorine, and this fluorine all move, but the phosphorus and the fluorine all stay put. So we have a value of 2 in this case. The next symmetry operation is the horizontal mirror plane. The horizontal mirror plane contains this fluorine, this phosphorus, this fluorine, and this fluorine, and when it's applied, these 2 axial fluorines both move. Everything else remains in place, and so we get a value of 4 for that operation. So in the case of an S3, we have a rotation along the threefold axis and a mirror plane applied, and so all fluorines are going to then move to positions. The only atom that stays in place is the central phosphorus, and so we'll get a value of 1. For a sigma V mirror plane, that will then contain this phosphorus and then 2 of the axial or both axial fluorines and 1 of the equatorial fluorines. And so 4 molecules will remain in place. These 2 fluorines are going to move, and so we'll get a value of 4. The next step is that we have to determine what the irreducible representation is for the X, Y, and Z directions. And so to do that, we can just look at the character table, and we can see that Z has A2 double prime symmetry, X and Y has E prime symmetry, so if we add all of that up, what we'll get is 1 plus 2 will give us 3 under the identity, 1 plus minus 1 will give us 0 under the C3, minus 1 plus 0 will give us minus 1 under the C2, minus 1 plus 2 will give us 1 under the horizontal mirror plane, minus 1 plus minus 1 gives us minus 2 for the S3 rotation, and 1 plus 0 gives us 1 for the sigma V. And so now we have the XYZ coordinate plane, and if we multiply that by the reducible representation that we determined for the atoms, what we'll get is the reducible representation for the Cartesian coordinates on each atom. And so if we do that, we'll get 18 under the identity, we'll get 0 under the C3, under the C2 we'll have negative 2, under the sigma H we'll have a 4, under the S3 we'll have a minus 2, and under the sigma V we will have a 4. And so now that we have the Cartesian coordinates for each system, we're then able to now determine what happens to all of the different movements that can occur in the molecule, because under the Cartesian we have the vibrational, the translational, and the rotational movement that occurs. And so the easiest way to apply the group theory to this to determine what the symmetries are is, instead of subtracting out the E double prime, A2 double prime, E prime, and A2 prime from this reducible representation right here first, and then determine the vibrations, we can just determine directly from here what all of the reducible representations are, and then subtract all of these out at the end, because it also gives us a pretty good check to make sure that what we have right here actually makes sense, and that we didn't accidentally forget a movement because if we don't have, let's say, an A2 double prime present in our final reducible representation, then we know something has to be wrong because there has to be that component as part of our system. And so the first thing we're going to do is we're going to look at the A1 prime and determine how many of those irreducible representations are present within our reducible representation. And so going through that, because it's the totally symmetric, it is just going to give us all ones in that case. And so we'll have 18 plus 0 plus minus 2 times 3 gives us negative 6, plus 4 times 1 gives us 4, minus 2 times 2 gives us minus 4, and then 4 times 3 gives us 12. So if we add all of that up and divide it by the order, and so the order in this case for D3H is 12, right? Because we have 1 plus 2 plus 3, and then 1 plus 2 plus 3. And so if we work our way through all of this, what we'll get is that we should end up with 2 A1 prime irreducible representations within the Cartesian system. So next we can then go through the A2 prime, and so in that case we now have 18 plus 0 plus, now we switch to a minus 1 right here, so this becomes now positive 6 plus 4 minus 4, and now this becomes a negative, and so we have minus 12. And so if we then add all of that up, what we get is that we have 1 A2 prime, as we would expect that we would have at least one due to the rotational symmetry, rotational movement. The next irreducible representation that we'll look at is E prime, and so in this case we'll have 18 times 2 will give us 36, plus 0, 6 times 0 gives us 0, 4 times 2 gives us 8, minus 4 times minus 1 gives us positive 4, and then 0 times 12 gives us, 0 times 12 gives us 0, and so what we end up with in this case is that we'll have a total of 4 E prime, right? So we'll have a value of 48 in this case. And so moving on, what we'll have is A1 double prime, and so looking at this, all of the last three are all going to be negative, so if we work our way through that, we'll have 18 plus 0 minus 6 minus 4 plus 4 minus 12. And so that'll then give us a total value of 0. Everything will cancel out in this case. Next, we'll look at A2 double prime, and so in this case we have a value of 18 plus a value of 0 plus, again, we're going to be switching this negative 6 into a positive 6 because of the negative number, so we're going to have plus 6, and then now we're going to have minus 4 plus 4 plus 12, and so that gives us a total of 3 A2 double primes. And so finally what we're going to be looking at is E double prime, and so in this case we'll have a value of 36 because we're going to do 2 times 18 plus 0 plus 0. This case now, because we have a negative 2, we're going to subtract 8. We're going to subtract 4, and then we have 0 here, and so we'll end up with 2 E double primes. And so overall, all of the movement that we're going to have in this system will be 2A1 prime plus an A2 prime plus 4E prime plus 3A2 double prime plus 2E double prime. And so if we look at the character table, we can see that we can subtract out from the translational component, and so this is going to be an E prime and an A2 double prime. For the rotational, what we'll subtract out is an A2 prime and an E double prime, and so in the end we'll subtract out the translational and the rotational, and what we'll get for the vibrational is 2A1 prime plus 3 E prime plus 2A double prime, or A2 double prime, sorry, plus E double prime. And so these are the symmetries of all of the vibrations. And so if we add them up, what we'll get is that we'll have 2 plus 6 right here, so that gives us 8, plus another 2 gives us 10, plus 2 more gives us 12. And so we have 12 vibrations that we determined right here, and so we can do our check again to determine how many vibrations we should expect. And so in this case, we have 3n minus 6 because it's not a linear molecule. N is going to be equal to 6 because we have 6 atoms in our system. And so we should expect to get 12 vibrations, which we do. We have that many right here, right? And so I think there was some confusion about how many vibrations the E's have. And so each E, right, is a 2D irreducible representation. And so that means that it has essentially 2 components to it. And so both of the vibrations that have E prime symmetry in one of these cases, they'll look different, but they will be energetically the same. They're going to be degenerate. And so if you look at an IR spectrum, you'll see a very strong peak, because underneath that peak, where you're looking at that absorbance, it's actually 2 individual peaks, because there's two different vibrations that are going to be occurring. But because they're degenerate, it'll only appear as if it's one. But we have two vibrations that fall under each E. And so that's how we end up with 12 vibrations. And so then if we look at and try to determine how many IR active vibrations we have, we can then see that all of the E prime and all of the A2 double prime are going to be IR active. And so we'll have a total of 3E prime plus 2A double prime, right? And so we should end up with, in this case, 5 peaks, right? But in total, what we'll have are 8 vibrations for this species. And so if we then go further and look at the Raman, we can see right here the Raman are going to be A1 primes, the E primes, and the E double prime. And so in this case, we're going to end up with a total of 6 peaks, but we will have a total of 1, 2, plus 6 is 8, plus 2 more is 10 vibrations that are going to fall within this grouping.